In this demo number 5, we present a multi-domain cybersecurity scenario in which a DNS server deployed in the CNIT testbed is the target of a DDoS attack. Throughout the demonstration, we will see how the horse architecture detects the anomalous behavior and automatically coordinates a mitigation response between both domains to protect the service. On this scenario, we can see the two infrastructures participating in the experimental scenario, the UPC and CNIT testbeds, interconnected within the horse environment. The target DNS server for the experiment is deployed in the CNIT domain. To simulate a distributed attack, we use two SCAPI instances acting as malicious user equipments (UEs), one located in the UPC testbed and the other within the CNIT domain itself. Both nodes begin to generate malicious DNS traffic simultaneously, sending high volumes of packets toward the DNS server with the aim of degrading or disrupting the service. After launching the script, the system automatically begins generating malicious DNS packets at high frequency. In real time, we observe how the traffic volume increases quickly, and the packets begin to propagate through the network toward the DNS server in CNIT. This sudden surge in traffic is precisely the anomalous behavior that will subsequently be captured by the horse monitoring mechanisms, triggering the automatic process for attack detection and mitigation. Once we have seen how the attack begins, this slide presents the general horse workflow that will be activated to respond to this situation. This diagram provides a global overview of how the different components of the architecture collaborate to transform the observed network traffic into automatic mitigation actions. The process begins with monitoring and data collection from the infrastructures, continues through the threat analysis and detection phases, and subsequently evolves toward decision-making, countermeasure validation, and the coordinated execution of the response across multiple domains. In the following slides, we will break down this flow step by step, analyzing each component and observing how the messages exchanged between them change until effective mitigation of the DDoS attack is achieved. Both infrastructures, UPC and CNIT, begin sending network measurements to the Smart Monitoring component. Smart Monitoring is responsible for collecting information from multiple domains generated during network operation, storing it, and sending it to preprocessing. On the left side, the terminal shows the shared folders between UPC and CNIT, where the PCAP files containing the network captures collected during the attack are stored. Simultaneously, on the right side, the Elastic Web Interface is displayed, where Smart Monitoring stores and structures the received information. First, we observe the increase in the number of records through the count query, which evidences the growth in the volume of monitored data. Subsequently, through the search query, the stored content is visualized, confirming that the captured packets are being indexed and prepared. At this stage of the workflow, the data collected by Smart Monitoring is sent to the preprocessing component. The objective of preprocessing is to transform the traffic captures into structured information prepared for security analysis. Once processed, the data follows two simultaneous paths. On one hand, it is sent back to Smart Monitoring for storage. On the other hand, it is forwarded to the DEMI component, which will use this refined information to detect anomalous behaviors associated with the attack. In the video, we are observing the internal operation of the preprocessing module. On the left side, we can see how the data arrives from Smart Monitoring, corresponding to the measurements collected during the DNS attack. After the processing is performed, the right side shows how the module sends the results to two different destinations. First, the processed data is returned to Smart Monitoring for storage. At the same time, the relevant information is sent to the DEMI, which will be responsible for analyzing this clean data to detect patterns and determine if there is malicious behavior. The processed data is sent from the preprocessing module to the DEMI component, which is responsible for threat detection. DEMI continuously analyzes the indicators generated from the monitored traffic, searching for deviations from normal network behavior. In our scenario, the anomalous increase in DNS packets originating from multiple domains triggers the detection mechanisms. The component performs an iterative internal analysis, refining the results and correlating the received information to confirm the existence of a coordinated attack. Once the anomaly is identified, DEMI generates a threat event and sends it to the DTE, where the evaluation and decision-making phase will begin to define the mitigation strategy. Following the detection of the attack by the DEMI, the threat event is sent to the DTE component, which is responsible for evaluating and contextualizing the security incident. The DTE analyzes the received information, classifying the type of attack, its multi-domain origin, and its impact level on the DNS service. Based on this analysis, the system generates a structured interpretation of the threat, which will allow for the definition of the most appropriate response. This evaluation is subsequently sent to the IBI. After receiving the attack evaluation from the DTE, IBI sent the information to CKB. Once the mitigation intent is defined, the IBI initiates communication with the CKB common knowledge base, sending information about the detected attack and its operational context. Based on this information, the CKB provides knowledge-based recommendations about possible mitigation approaches for the multi-domain DDoS attack. These recommendations guide the response, while the RTR component later defines the operational playbook and concrete mitigation actions within the HORSE workflow. Return to IBI intent-based interface component, which acts as the central coordination point within the HORSE architecture. After receiving the attack evaluation from the DTE, the IBI transforms the technical information into a mitigation intent and coordinates the response with the rest of the system components. In the video we can see, on one hand, the logs and messages that the IBI exchanges in real time, and on the other, the interface confirming its successful connection to the HORSE architecture. The system registers a detected attack attempt, identifies the scenario as a multi-domain attack, and shows how threats automatically transition to the mitigation state, thus initiating the coordinated response between the UPC and CNIT testbeds. After receiving the proposed mitigation strategies, the IBI sends the response intent to the CAS, compliance assessment, component for evaluation. CAS analyzes the proposed actions, verifying that they comply with security policies and do not generate negative impacts on services or infrastructure. Once the solution is validated, CAS returns a positive evaluation message to the IBI, confirming that the countermeasures can be safely applied and allowing the activation of the mitigation process to continue within the HORSE workflow. Once the mitigation is validated, the IBI sends the response intent to the RTR, Reliability, Trust and Resilience Provisioning, component, which is responsible for transforming the defined strategy into concrete operational actions. The RTR automatically generates the necessary countermeasures, such as traffic rate limiting configurations or route blocking in both affected domains. These actions are subsequently sent to the EPM, End-to-End Proactive Secure Connectivity Manager, which handles translating them into specific technical configurations and applying them to the infrastructure, thus executing the attack mitigation in a coordinated manner between the UPC and CNIT testbeds. After generating the mitigation actions, the RTR sends the instructions to the EPM, which is responsible for specifying and orchestrating their deployment within the infrastructure. The EPM translates these decisions into technical actions applicable to the network and services deployed in both domains. Finally, the resulting policies and configurations are sent to the DOC component, which applies and distributes the mitigation measures across the UPC and CNIT infrastructures, ensuring that the response to the attack is executed in a coordinated and effective manner. In the video we can observe the operation of the EPM. The different endpoints available for action orchestration are shown on the left, while the responses received after executing the requests appear on the right. In this final phase, we can see how the DOC component applies the mitigation actions to the infrastructure. The video shows the arrival of the block_use_multi-domain policy, which executes the blocking of the attacking nodes in both domains, thus completing the coordinated DDoS attack mitigation within the HORSE architecture. This concludes the demonstration, showing how the HORSE architecture is capable of automatically detecting, analyzing, and mitigating a DDoS attack in a multi-domain environment. Through the collaboration between its components, the system enables the transition from traffic monitoring to the effective application of countermeasures in a coordinated manner, ensuring service protection and infrastructure resilience. Thank you very much for your attention.